I welcome all of you participants to this session of the International Short Course on Advanced Physics. The topic of this session is computational physics, and my focus in this session, after introducing the participant to what computational physics is and what are the various fields in computational physics, will be to introduce them to Julia language. It's a new and modern language, and why I find it to be one of the best platforms around for computational physics in the current date. I'll also explain in this presentation the pitfalls of computational physics, what to do, what not to do, give a few references, and obviously give the participant, if they are uninitiated, a starting point for computational physics. Is the primary goal of this presentation. So without consuming any more of your precious time, let me just start this presentation. So this is my topic, Introduction to Computational Physics. This is the famous Lorentz attractor. For those of you who do not know the history behind this, this is historically very significant for computational physics because this was the first system that showed that if you put something on a computer, something physical in a computer, you can get different results than what common sense tells you. And this is me, the speaker, Deepak Jala. I'm an assistant professor at the organizing institution itself. As a brief outline of my talk, I will start with the what, why, and how of computational physics. Then, in the next video, we will go to the introduction of Julia along with its various pros and cons. And lastly, we will encode physics problems in Julia, and we will also tell you what not to do when you're doing computational physics. There will be references and as well as acknowledgements because no human effort is a single man effort. We have to acknowledge other people as well. So, what is computational physics? Now, this is a question that should come to most few who are uninitiated, that what is computational physics. Common sense tells us computational physics is I'm using a computer to solve physics problems. And you're right, but that is not the more complete definition of computational physics. Because if it was simply I'm using computers to solve physics problems, it would be nothing more than theoretical physics. It will not be an own standalone branch of physics as it is today. Because then it is just theoretical physics input into the computer. So what it is, I will explain in the following slides. Now, um, this is, I'm paraphrasing from Wikipedia. Computational physics is the study and implementation of numerical analysis to solve problems in physics for which a quantitative theory already exists. Now, what this definition tells you is, say you take quantum mechanics. The quantitative theory of quantum mechanics already exists. It is quite well known, right? So you can either take the Schrodinger picture, the Heisenberg picture, or the interaction picture, whichever suits you or your application. And its mathematics and its formalism is pretty well defined. You don't have to invent anything there. So that is what is meant by problems in physics or its quantitative theory already exists. Now, what is meant by numerical analysis? So suppose in physics, mostly what we do is we try to get a differential equation and then integrate it and get an answer. So how do you integrate a differential equation? You can do it by hand for certain set of differential equations on pen and paper, but our focus is computational physics, so we must understand what is meant by numerical analysis in that context. So we use methods such as the Rangekota method, we use the quadrature methods, we use numerical methods which will help us carry out these integral operations, right? This is what is meant by numerical analysis. Now, numerical analysis is not purely uh, numerical integration. There are other methods also that we use, right? So sometimes we have to take out fractal dimensions. Sometimes we have to take out box counting dimension, limit infimums. Lot of other mathematical analysis is rigorous mathematical analysis is required in computational physics. So that being there, but there is one area where this definition falls short, and that is turbulence, and I'll explain that later. What is turbulence? Now, some people call it the amalgamation of physics, maths, and computer science, and personally, they are more or less right. But I find that description lit little belittling of computational physics, because I find that it is more a extension of the thought experiment that was popularized by Albert Einstein. So this itself is a very interesting story. Albert Einstein was as some of you may know, very unhappy with the way quantum mechanics shaped up, and he wanted to have an alternative explanation for it. For what? For the success of quantum mechanics in when it comes to explaining real world phenomena, experimental data. And his problem was that all the experiments were very coincidental with the quantum mechanics of the time. Those who are not coincidental could be accounted for with a little bit of modification to quantum theory. So the Stark and Zeeman effect, LS coupling, right? So he said, since there is no experiment that can show what I want to show, let me concoct an experiment in my head, which I cannot, which is not physically feasible with today's technology, and let me show that quantum mechanics is incomplete. But as history has proven that he in fact showed quantum mechanics is rather complete and is rather unique as well. So I find it an extension of the thought experiment. Why it is needed? We were fine when pen and paper physics. Why is this analytical? Uh, why is this branch of physics needed? I mean, we were fine, right? We solved all the sort of problems from ranging from classical physics to high energy physics using pen and paper. So what's wrong? So if I were to put it in a very concise way, those problems which you can solve with pen and paper, mathematically they are deemed analytical, and that's fine. But why is that problematic? Because the world, the real world, the outside world, the world that exists outside physics textbooks, that still adheres to physics textbooks, is not analytical. There is non-linearity in differential equations. There are complicated differential equations, and the use of approximations and linearizing those differential equations would be fine up to the point that several observed physical phenomena were not glossed over, were still included. But as our understanding of the universe increased, we realized, oh, if we take only the analytical equations and solve, we are glossing over several real world phenomena, and these real world phenomena cannot be understood until we understand this non-analytical part of those equations. An example of that would be double pendulum logistic map. Logistic map was especially frightening for people because it was nothing more than the mapping for insect population over generations. And it led to such complex behavior from such a simple model that people really thought, okay, there's something different going on. Two, it reduces tedium in theoretical physics. I mean, I don't know how many of you know this, but there was a time when I was working on quantum information, and what we used to do was that we used to have a 4-qubit state. So if you have a 4-qubit state with a Bryan cat, which means the space is having how much? Two states, right? Each bit has two states, 0 and 1, and there are 4 bits. So that would mean that the state space would be a tensor product. So there would be a possible 256 term long algebra if I want to find its density matrix, and sorting through those, finding which are zeros will become a big problem. So what do we do then? If you have large algebra that you cannot solve, that solving with hand becomes very tedious. You use computer algebra systems like Mathematica and MATLAB and Maple to solve for these. And an example of this is a lot of GTR calculations can today be done in Maple. Now, GTR hand calculations can be done today in Maple. It can also reduce costs of experimentation. Now, what do you mean by cost of experimentation? Suppose I am designing a pressure cooker, right? So what I'm using is steel, and I'm increasing the pressure in the pressure cooker, and I have a safe environment in which I increase the pressure till the pressure cooker or some component of the pressure cooker gives, and then I find a way to reduce that pressure rating. And I say for this pressure rating, if you use gas burners, commercial gas burners available in most homes, this pressure cooker should be safe. But when I'm doing that, one pressure cooker may get destroyed. So this is called as destructive testing. So for a low tech industry like pressure cooker, this is very cost effective. But take the example of Boeing. When they design a new jet engine and they want to test the materials of that new jet engine, it will be highly detrimental, cost detrimental, because what will happen if you build a new jet and you test it in the real world? You'll need a very intrepid test pilot who does not value his life to test it to destruction. B, a assembled Boeing model, jet model, when in production run, costs a few $100 million. So you can see that running those kind of tests in the real world is very expensive, prohibitively expensive, and therefore computer aided testing by the use of computational physics is the way to go. And when you are dealing with turbulence where the mathematical model is not stable, only computational physics can probably provide some insights. Other fields do not. And this is why till date there is no analytical solution for the Navier-Stokes equation across all runs, subsonics, hypersonic, etc. This is a frozen in time image of the double pendulum. So how it is done? There are two approaches: use of programming languages and use of computer algebra systems. Now, most people oscillate between these two approaches, but I'm going to further show that it is possible to do have it all. So programming languages are like an F1 car. They are very fast for the task they are designed for, right? They're the fastest thing out there, like C. For running things in a loop, it is the fastest thing. There is no doubt. C++ doesn't come. Uh, C is the gold standard. Now, C does not have inbuilt tools, right? So suppose I want to deal with complex numbers. Suppose I want to do Fourier transforms. Suppose I want to do wavelet transforms, things like that, like Laplace transforms, integration. I have to either construct these tools by scratch or I have to go through a very complicated GNU license. I have to install GSL and do that. And the problem with that is GSL is not supported natively. Right? So suppose I want very high precision numbers because I'm running a large data set and I want to ensure that there's no truncation error. Then I can use MPFR and C, and it becomes very cumbersome because I cannot multiply numbers directly, add numbers directly. I have to use MPFR functions, which slows down my work considerably. So what people do is they run one section in one programming language, then they do the analysis in another software, and this creates a lot of runaround. Computer algebra systems like say Mathematica, I can run my problem, I can plot its solutions, I can do its Fourier transform, I can do its Laplace transform, I can do its wavelet transform, and take out its coefficients in one package. But because computer algebra systems have so much baggage, they have to, every time they boot up, they have to carry so much baggage. What happens to them? They become very, very slow. How slow? Across all tasks, there are certain tasks that are used to measure the speed of programming languages. Uh, Mathematica was thought to be 120 times slower than C, whereas MATLAB was turns out to be around 5 to 600 times slower than C. So, so the speed you lose is quite considerable. But still, you prefer this sometimes because the second option sometimes because of the compatibility issues. So that's the old saying: kids pick and choose, adults want it all. So what does the adult physicist want? High speed, high level language that can have a lot of toolkits in its arsenal. And the answer came in form of Julia, which started development in 2009, currently in version 1.5. Right? And best part, it's free, completely free to use. It's completely free to edit. It's completely, if you feel confident enough and you are competent enough, you can write packages for Julia and post them on GitHub. And people will use your work to, you know, push their research forward. And recently, it's been widely used in several high tech fields. So I'll discuss that in the next slide, in the next video. Till then, I take your leave and see you in the next video.